Hello, my name is Benjamin Kolicic, and today I'm going to talk to you about my project, Stochastic Disorder Problems, which is based on a paper by Shiryaev with the same name. I'm currently standing outside Newcastle Cookie Factory, and inside this cookie factory there's a chocolate chip dispenser that dispenses chocolate chips according to some distribution. At some random point in the future, this dispenser is going to break, and it's going to start dispensing chocolate chips according to a different distribution. This could potentially lose the cookie factory money, and so we want to know about it. This is a stochastic disorder problem.
Shiryev's original paper is very comprehensive, covering all sorts of stochastic disorder problems in both discrete and continuous time. My project focuses on discrete time Bayesian disorder problems, and the reason I've done this is twofold. One is to kind of fill in some of the details that he missed, and two, to actually make these problems more approachable. So the requirement for this project was to cover ST409. The goal of this project is actually to bring these problems to the general undergraduate who hasn't covered ST409. Now, this being said, during this presentation, I have to use a lot of technical information, but don't be worried. In the original project, I bring everything up from the basics. So let's begin. So the mathematical definition of a disorder problem, let's look at it. At some unknown time theta, which we call the disorder time, the mechanism generating our data changes. Either a machine wears out or a market regime shifts, whatever you like. We see these observations, x1, x2, x3, that arrive one at a time, maybe daily, and we have to decide whether to stop our mechanism or not online. So we can only use information on the present and the past. Before the disorder time theta, we assume we get IID draws from some known density, f infinity, and from disorder time theta onwards, we assume that we have IID draws from a different known density, f0, and just remember we only see the data. The disorder time theta is latent or it's hidden. Now this can introduce two problems. Either we stop the mechanism too early and we have a false alarm that might cause a penalty, or we stop the mechanism too late and we have like some sort of costly detection delay. And so we want to try and generate a theory that tries to minimize one of these two errors. This is just a kind of more graphic example of a disorder happening in real life. So we have we see that these gray dots are what we expect, and then on day 40 we have a disorder, and we see that the distribution changes and the mean is slightly higher. Now, Shiryaev introduces his G model, or the Bayesian model, which treats the disorder time theta as random with a geometric prior. And so another way of saying is that the disorder strikes on a day with probabilities p, independent of the past days. Now, there's a couple benefits to this. The first is that the disorder time is memoryless, right? The break is never due, we're never expecting it. And this assumption, we'll see later, actually makes the problem exactly solvable. Without this, we have to go through a lot more difficulty and obstacles. Another definition, an alarm rule is a stopping time tau, and it's the decision to stop by day n, and can only use information up to and including day n. Now, the natural thing to track in these problems is the posterior probability or the posterior belief that our disorder has already happened. So this is exactly what pi n is. Now, it turns out that the algebra is slightly nicer if we use the posterior odds phi n. And one of the first results that we cover in the project is actually that we can connect phi n with this recurrence. And so we can see that the important part here is actually this likelihood ratio in red. And this just measures how surprising the data coming in today is. And more surprising data pushes our belief that the disorder has already happened up. And one of the consequences of this memoryless disorder time prior being geometric is that our posterior probability that the disorder has already happened becomes a homogeneous Markov chain. Now, to define this cost function, we use Shiryev's variant A of the problem, and there's variant B, C, and D, but we'll look at those a little bit later. And the whole goal of this is to minimize this cost function, which comprises of the false alarm and the expected detection delay with this kind of multiplier C in the middle, and we want to minimize this cost function over all stopping times tau. The constant C is an exchange rate between the two mistakes. A large C makes waiting and the detection delay expensive, and a small C makes false alarms relatively worse. As mentioned, Shiryaev also introduces variants B, C, and D, which drops the prior of the disorder time and leads to certain minimax theories. But as I said, this project focuses only on variant A. But we can see from this cost function, or this risk function, that there are two problems. Remembering that the disorder time theta is hidden, we only see the observable data, neither the indicator that tau is less than the disorder time, nor this expected detection delay is kind of observable at time tau. To answer some of the questions in the previous section, we need some optimal stopping theory. The general optimal stopping problem involves these payoffs Gn that we see every day, and we can only observe payoff Gn at time n, and the goal of the problem is to optimize the expected payoff over all stopping times. Now, if we have kind of a fixed end date, we can do something very clever, which is to define Sn, and we set Sn equal to the payoff on the final day, and we perform backwards induction, where each previous Sn is just the maximum of the current payoff today and the expected future payoff given the present information. And this leads to a very simple stopping rule, where we stop the first time the immediate payoff, Gn, matches Sn. And the project proves in full that no rule can beat this. Sn is known as the Snell envelope, which is the smallest supermartingale dominating the payoffs. But what if we don't want, or we don't have a finite time horizon? Well, we need an infinite horizon, but the problem with that is that we can't use the same strategy because there is no, end date to perform backwards induction on. So we have to introduce a little bit more theory, the essential supremum, basically to extend to the infinite time horizon. Now, if the payoffs depend only on the current state of a Markov chain Z, everything collapses to one value function on the state space, where the value of a specific state Z is just the maximum of the payoff of that state and the expected value of continuing the chain from that state. And this is called the Wald-Bellman equation. And this is really nice because it splits the state space into two separate regions, the continuation set C, where the expected value of continuing the chain is worth more, so we let it continue, and the stopping set D, where the expected value of continuing the chain is not worth more, so we stop it. The optimal rule here is just the first entry rule now, where we stop the moment that the chain first enters the stopping set D, and now all problem-specific work from this point on is just to find the shape of D. Now we will use the optimal stopping theory from the previous section to answer the Bayesian disorder problem from the first section, all culminating in something called the threshold theorem. One of the major results from Shiryaev's work is called the reduction to standard form for the Bayesian disorder problem, where we see the Bayesian risk on the left-hand side, which we talked about in the first section, and the reduction to standard form theorem says we can manipulate this risk into something on the right-hand side, which namely removes the disorder time theta entirely for every finite stopping time, tau. We notice that 1 minus pi tau is the conditional probability that the alarm was false, and each pi k is the conditional probability that we are already late, so the disorder has already happened. So the sum of these accumulates this expected delay. Well, why is the reduction to standard form theorem important to us? Well, it allows us to transform a Bayesian inference problem into a standard optimal stopping problem for this specific Markov chain, pi n. As mentioned, the main theorem of this section is the threshold rule, in which Shiryaev says, in the IID observation model with geometric prior, the optimal stopping time is tau star, which is the first time that our posterior probability that the disorder has already happened, pi n, exceeds or is equal to a threshold pi star, which is dependent on C, P, F0, and F infinity. In other words, we stop the first time our belief crosses a fixed level pi star. The theorem also says that the pair of the value function and the threshold pi star also solves a discrete free boundary problem, also known as a Stefan problem. This allows us to use an iterative method to find what pi star is. The theorem also tells us that we have an explicit lower bound on pi star, which is that pi star is greater than or equal to p over c plus p. We notice that our value function v is concave and lies on or below the line 1 minus pi and meets it at pi equals 1. We recall that a concave function trapped beneath the line can only touch it along a single connected stretch. So the connected set is the terminal interval pi star to 1. And this gives us quite a nice graphic for what we talked about in the previous section of the continuation set on the left and the stopping set D on the right. Now let's look at an example. Let's use the distribution of no disorder, F infinity, to be the standard normal, and the distribution for disorder, F0, to be normal 1, 1, with a geometric prior of 5%. If we iterate the stop or continue comparison until the convergence of pi star is reached, we get these different results for different delay costs. So we're looking at delay cost 0.01, 0.05, and 0.2. We notice that if the delay is cheap, in the case of 0.01, we are patient. We demand that we are 96.7% certain that the disorder has happened before we reset the mechanism. And if the delay is expensive, the alarm fires on incomplete evidence, right? We only need to be 40% certain for us to reset the mechanism or stop this process. We also notice from our lower bound section that our lower bound of P over C plus P is quite weak. And this is something we can see in this graphic here, where for kind of middling values of C, we are quite far away as a lower bound. Now let's look at a financial application of the above theory, the problem of optimal stock liquidation, or in other words, when should an investor sell their stock? If we assume that daily log returns are normal, which is a standard assumption to make, and we define a bull regime to have positive drift, mu1 is positive, which switches permanently at an unobserved disorder day theta to a bear regime, mu2, which has negative drift, and we make kind of all the other standard assumptions that are made in financial mathematics, such as constant volatility, and we make the assumption that we've been making the entire project that our disorder day theta is geometric, we see that this is exactly the disorder problem that we were describing above, where this kind of mechanism of no disorder is the bull market with positive drift, and the disorder happens when we switch permanently to the bear market with negative drift. We also see in this situation how both a false alarm and a delay after the disorder occurs can be kind of financially bad for us, where a false alarm means bailing out of a bull market, so a market that's increasing still, and the cost of keeping or holding the stock after the disorder happens has financial consequences because we're holding a losing asset. From the above theory, we've been told that we should sell on the first day your posterior probability of the break reaches pi star. Now, using some numbers and performing a similar analysis to what we did above, if we set mu1 to about 20%, mu2 to negative 20%, and our annualized volatility to 30% with a geometric prior of 1 over 60, we notice plugging in these values, even though they seem quite intuitive values to plug in, we notice that the gap between daily mean returns is under 1/10 of the daily standard deviation. So a single additional day gives us very little information on whether the disorder has actually occurred or not. So we've got a few values here for different delay costs. So as C is 0.005, 0.01, and 0.02, we have these different threshold values pi star. Now, one thing to notice here is that our lower bound is much tighter because it's built from this kind of one-step comparison, stopping now versus taking on one additional observation. And when a single observation is very nearly uninformative, the next piece of information is worth as much as all the future data combined. So this kind of one-step bound nearly equals the true value. This is just a graphic to show as an image what's going on. So we see on the top is our stock, and on the bottom is our posterior probability that the disorder has happened, pi n. And we notice that as the disorder occurs on day 60, how long it takes for our model to notice and rise above the threshold of 0.6. Now, running this simulation using Monte Carlo estimation 20,000 times, each time we draw a disorder day theta from the prior, which is geometric, 1 over 60, and we generate these returns in the appropriate regimes, then update the posterior until it crosses pi star is equal to 0.644. So this is the situation in which our delay cost C is 0.01. We notice that 33% of runs end in a false alarm. The mean delay after the disorder occurs is 34 days, And the empirical risk, which we got via this iterative formula, is very similar to the theoretical risk V naught, which is 0.564. So as I mentioned, we see that roughly a third of the time the investor is shaken out of the bull market by an unlucky run of bad days. So this is the false alarm situations. Otherwise, a month and a half of bear market data is needed to be 64% short. So this is our threshold pi star. At the same false alarm rate, Q-sum, which is a different variant that Shiryaev talks about, the Q-sum's mean delay is 49 days. So using this geometric prior of 1/60 or whatever we set it to in our real world example saves us about 3 trading weeks of bear market data. Now let's talk about some of the limitations of using these methods in financial applications. Well, one major limitation is that we know that real returns aren't, one, normal, and two, real volatility is not normal either, and we know that volatility shows clustering and heavy tails. So this is one of the main problems that we already have. Our assumption for how the returns are distributed are wrong. We also can say that both our densities aren't known exactly, but we're assuming that we know them exactly. So if we even misspecify our disordered distribution F0 or our no disordered distribution F infinity, this will bias the likelihood ratio every single day. So, day by day, we'll just be compounding these distributional errors. The geometric prior that all of our theory is based upon may not, be a good prior either, but the problem is that using any other prior makes the recurrence relationship that we talked about in the first section time inhomogeneous and turns the constant threshold pi star that we saw in the threshold theorem into a moving boundary. So this makes things a lot more complicated for us. We can also say that the delay cost C is not given, and it must be elicited from some sort of practitioner, and that value of C may depend on their use case or their capital or whatever have you. In terms of moving forward from the project or moving how we could improve in the future, well, I would quite like to cover the continuous time theory that Shiryaev talks about and the minimax variance C and D, as well as potentially looking at actual real market data to test this kind of liquidation problem on historical data. Of course, this would need to be given the same treatment that I gave to previous parts in variant A, which is namely 1, coloring in some of the missing details, and 2, bringing the entire part, the entire bits that I want to cover in the future down to the undergraduate level, someone who hasn't covered ST409. So why read my project? Well, firstly, it's a self-contained survey of the discrete time Bayesian disorder problem aspects of Shiryaev's stochastic disorder problem work, and as I mentioned, it's readable with undergraduate probability only, no ST409 required, which was a requirement for taking on the project. I also cover full proofs of the backwards induction theorem, the reduction theorem, and the threshold theorem with additional details from the source text omitted. I also made 2 expository contributions, one of which being an elementary 2-step Bayesian derivation of the posterior occurrence, which we saw in the first part, and the perspective function proof of concavity, which was stated without proof in the source, which we covered in the third section. I also go into more depth about the numerical examples that we use. For example, I kept mentioning today about how we calculate pi star from value iteration. Well, there's the algorithm for that in the paper. I go more into detail about the 20,000 simulation Monte Carlo estimation, which we also show that it agrees with theory, as well as digging deeper into some comparisons with different variants, namely the Q-sum variant. So just to recap on what we covered today, and what's covered in the project, we first looked at the disorder G model, or Bayesian model, as it's called in the paper, which we looked at 2 regimes and a geometric prior on the disorder time theta. We talked about the natural thing to track, which was pi n, which is the posterior probability that the disorder has already occurred. We looked at the fact that it turns out that it's a Markov chain, and we also derived the 1-step recurrence. We looked at some optimal stopping theory, as well as the reduction theorem, and the fact that we used the fact that the value function was concave to derive some facts. And we ended up with the threshold theorem, which says we should stop when our posterior probability that disorder has already happened, pi n, exceeds or is equal to the threshold pi star. we also use that to apply the theory to the financial market. Thank you for listening. I've been Benjamin Kolicic.